Good morning. Um, just about afternoon. Actually, it's 12 noon exactly. So good morning and good afternoon. Um, Hope all of you are doing okay. Um, Communicating from my kitchen table, where I have been communicating for the last week and a half. So I hope you guys are doing okay. I'm hoping to have your second exams back on Thursday. And then actually, I have a doctor's appointment on Thursday morning, and I have surgery scheduled for the following Tuesday. But let's see what we can do to try to communicate. So Dr. Habdas will be my liaison for the next week or two. But as I said, I will try to get your exams back on Thursday, and we're into the final stretch here, people. So let's leg it out. I really thank all of you for being so wonderful through this multiple transitions: COVID, PJA, tearing his Achilles, and so let's see if we can end the semester in fine fashion. Anyway, I'm going to start chapter 9, and I hope to finish chapter 9 or at least by Thursday. There might be 5 or 6 parts. So again, I'll try to upload modules that are, usually 15 or 20 minutes long. Sometimes they're longer, but that's how it will go. Okay, so anyway, let's go. Chapter 9. So this chapter deals with linear momentum, and we need a couple of things that will lead up to that. So let's begin. The first is the notion of center of mass. So if we imagine we have two masses, m1 and m2, and if we asked on the average where all that mass is concentrated, then we could use just a weighted average. And so if we were to look at that, the x center of mass, again, if this is the x direction, this is the y direction. The x center of mass would be nothing more than a weighted average. And so that would be m1 at x1 plus m2 at x2 divided by the total mass, m1 plus m2, which then would be equal to m1 x1 plus m2 x2 over the total mass, capital M. All right, and that's there's nothing magical about that. That's, again, if you think about weighted exam scores and you were asked to find what the average score was, a similar formula would emerge. Okay, so if we were to do that, perhaps the center of mass is going to be somewhere here, and that makes sense because, again, if M2, looking at the picture, is greater than M1, then the center of mass is going to be closer to where most of the mass is concentrated, in this particular case, M2. And so there's nothing magical about that. Again, just to complete this drawing, well, actually, let me erase this. In this particular case, x1 would be equal to 0 meters, for instance. And then this distance here would be x2. Nothing magical about placing the origin on one of the masses. We could have very easily redrawn this scenario so that M1 is here and M2 is here. And again, this would be X1. This would be X2. And again, the center of mass would be here. And relative to the two objects, it would be in the same place. Okay, so there again, we can write that X center of mass would be equal to M1 X1 plus M2 X2 over the total mass. We don't need to have just two objects. We can have as many as we want. We're dealing with chemical systems. We can have Avogadro's number of particles. And so we have a shorthand for that. So we have a summation notation. This would be I is equal to 1 to n, where n is the number of particles, the m sub I times x sub I over the total mass. Since the total mass is a constant, we can actually take it out of the summation. And so in its most elegant form, you would have the center of mass along the x coordinate would look like so, okay? And again, nothing magical about x. We would have corresponding formulae for the center of mass along the y-axis and the z-axis. Okay. Z center of mass. And the problems that I've assigned will highlight, doing these not too complicated calculations. Okay. So we can actually get more elegant than this. And this is a picture we're going to use throughout this discussion this morning. And so imagine that we have a three-dimensional coordinate system, and we haven't really dealt much in three dimensions this semester. Okay, so we have a three-dimensional coordinate system. And we can very well imagine that we have, an M1, an M2, an M3, and perhaps an MN, all the way out to MN. And each of those will have a corresponding radius or coordinate. This would be R1. This would be R2. This would be R3. And this would be Rn. And so we could write the center of mass then in a vector equation. Okay, and so we can say that R center of mass then is going to be 1 over the total mass, the summation I equals 1 to n, and this would be then m sub I, r sub I vector, okay? And so that's in its most general form, all right? And this picture then is going to be important, going to follow us along throughout the discussion this morning. I should point out that there's something special about at least this particular case, is that these are discrete masses, right? So these can be considered to be point masses at each of these coordinate vectors. One could imagine one could imagine a continuous distribution of mass, and we're not going to deal with that specifically, and you can read about it in the chapter. But you know, we can imagine a distribution of mass, and again, how do we deal with that since it's not discrete? And you'd have to deal with this through integration. And so, you know, the x center of mass would be 1 over the total mass, the integral then of x dm, and similarly for y and z. Okay, and those calculations are usually usually a little bit more complicated, but let's stick with the discrete masses for now, because that will provide us with all of the important physics that we need to understand in this chapter. Okay, so I've really been almost lying to you all along, and you will recall that most of the semester I've said that Newton's second law was only good for one object at a time, right? So we've been writing F net is equal to that object's mass times its acceleration. And when we had a multi-object system, multi-particle system, we actually treated each of those objects separately, and then we had a system of equations that we eliminated. Usually the tension, if we were dealing with things connected by strings, we've eliminated the tension to find the acceleration. But Newton's second law actually can be recast to talk about systems of particles, 2, 3, Avogadro's number of particles, right? So actually Newton's second law is more powerful than I originally intimated. And so actually we could write Newton's second law for a system of particles as F net is equal to the total mass of that system times the acceleration of the center of mass of that system. Okay, and so that's not easily seen, but let's spend a few minutes and let's derive that. Okay, so from above here, right? So from this equation, we can get that the R center of mass, and again, this should be a vector, right? R center of mass is going to be then equal to 1 over m. Okay, it'll be then m1 r1 plus m2 r2 plus all the way up to mn rn. All right, and let's multiply both sides by the total mass. So this will be capital M, total mass of the system. All right, so this is the total mass of the system. And again, let's just let me just scroll back here, right, to this figure, because this figure, as I said, is really important. So the system then, sometimes notability is, so the system then can be considered to be this assemblage of masses, right? So this is the system. We use that word a lot, okay? So these masses, M1, M2, M3, all the way up to Mn, right, are going to be considered to be the system of particles, okay? And each of these particles could be moving independently of all the others, right? And there's going to be forces involved. And so let's tease all of this. Let's tease all of this out. So, so M is going to be the sum of the masses. And what I'm going to do is I'm going to take the derivative. I'm going to take the derivative with respect to time, both sides of this equation. Now, masses are constant. This will be dr1 with respect to time, plus m2 dr2 with respect to time, plus all the way up to drn with respect to time. And we recognize then that the velocity, by definition, is the first derivative of the displacement. And so then v1 is equal to dr1 with respect to t. v2 is equal to dr2 with respect to t, and so on and so forth, okay? So that this then becomes the total mass of the system. This then becomes the velocity of the center of mass is going to be equal to m1 times the velocity of v1 plus m2 times the velocity of v2 plus all the way up to m sub n, the velocity of vn. All right. So no, again, no magic there. I think I've used the word magic 3 times. So just a little calculus. So I can take the derivative with respect to time again, right? So then this is going to be the derivative of the center of mass velocity with respect to time. And I should point out, right, scrolling back, slowly scrolling back to this diagram, right? So somewhere here might be, right, this might be the center of mass. And so this then would be the R center of mass. Okay, so that might be the center of mass of all these particles. Okay, and the center of mass does not necessarily need to reside on any particular particle, and we saw that back in this simple case where we had just two objects. The center of mass was actually at some point in space between them. Again, closer to where most of the mass was concentrated. Okay, so then continuing on here then, this then is going to be equal to m1 dv1 with respect to t plus m2 dv2 with respect to t plus all the way up to m sub n dvn with respect to t. And we know that the acceleration, instantaneous acceleration, by definition, is the first derivative of the velocity. And so a1 then would be the first derivative of the velocity of 1. va2 would be the first derivative of the velocity of mass 2. And this process would then continue on. Okay, so so what we have then is that we would have the total mass times the acceleration of the center of mass is going to be equal to m1 times the acceleration for mass 1, m2 the acceleration of mass 2, all the way up to mass n times the acceleration of mass n. Okay, and we recognize what's on the right-hand side here, right? This is going to be the net force on object 1. This is going to be the net force on object 2, plus all the way up to the net force on object 3. Okay. Now, what we have to appreciate is that the forces on these objects, right, are both internal and external. Okay, so let me scroll back to that all-important diagram, which is not in the textbook. Okay, and so let me just select another color here. And so, you know, M1 and M2 could very well be interacting. Okay, and there could be a force of interaction between them. And let's just say it's attractive. And so then one would have this force, which we would say that's the force on 1 by 2. And then you can have a force on 2 by 1. And these forces, right, these internal forces, why are they internal? Because they're internal to the system. If we look at the brackets here, these forces then are internal to the system, okay? And they're typically going to be interactive forces that are equal and opposite, right? And act on different particles. And so they constitute a force pair in Newton's third law sense. And so these internal forces will cancel. These internal forces will cancel in the system. Okay, and there might very well be other forces, right? There might be gravitational forces on each of these objects. Okay, so there might be gravitational forces, and they don't cancel because there's nothing to cancel them. So they will truly be external forces. Okay, so the internal forces will cancel. Okay, these there could be other forces, some other external forces, and they will not cancel. Okay, because M1G and M2G are in general different. Okay, and then there's nothing to offset them. All right. So what happens at the end of the day is that all of the internal forces here will cancel. And what it leaves us then is then F external of 1 plus F external forces on 2 plus F external forces on N. Okay. And so then this side just merely becomes the sum of all external forces on the particles of the system. Okay. And we know what we've been calling that, right? Up to date, right? We're just going to be calling that F net. Okay. And I'm just going to put up here for one and only time that this is going to be F net, the sum of all of the forces on the system. It's going to be equal to the total mass of the system times the acceleration of the center of mass. And you'll see this in your text as F net is equal to the total mass times the acceleration of the center of mass. And this is the formula that we set out to prove. Teased it apart, right? You know, we teased it apart, understanding all of the steps in here is important. I would never ask you to redo that derivation, but the conclusions here are crucially important, right? They're crucially important. So let's go back and look at single particles, right? Just single particles for an instant. And we're going to define a new entity. Okay, so we're going to define a new physical entity. And that's going to be called the linear momentum. And the linear momentum P is going to be equal or defined to be the object's mass times its velocity. Okay, so we have an object moving in three-dimensional space. Here's an object moving in three-dimensional space. And so here's the object's mass. Then the linear momentum is going to be the product of the object's mass times the velocity. Now, a couple of things to note, all right? One is that mass is a positive scalar. Mass is a positive scalar. Obviously, V is a vector quantity. Okay? And because of this deceptively simple equation, we can say unequivocally that the linear momentum and the object's velocity share the same direction. Okay? So linear momentum and velocity would share the same direction. And this is not unlike, right? This is not unlike Newton's second law, where we said F net is equal to mass times acceleration, again, for a single particle, right? We noted that the force and the acceleration were in the same direction, okay? So that's one important note. The other is the units. Let's take a look at the units. So the units are going to be units of mass, which are kilograms, velocity, meters per second. So this is a kilogram meter per second. And sad to say, we need to carry that around. So in force, we defined the Newton to be a kilogram meter per second squared. We don't do that here. So we're just going to carry around kilogram meters per second. The last thing is YP. YP for describing the linear momentum. Why not L? Right? And actually, it's going to be either more strange than that. We're going to use L to define the angular momentum, okay, which is, again, kind of strange. Why didn't we use L for the linear momentum and use something else for the angular momentum? Well, this actually goes back to an antiquated word, which was actually used by John Baridan. It was a, I guess, later Middle Ages, and he actually coined the word impetus, which is related, right? Which is, erase that, which is related to linear momentum. And the Latin word for impetus is petere. Hence P. Okay. So let's stop right there for this particular discussion. I'll upload this and we'll move on to linear momentum for a system of particles. and talk about impulse. All right, guys, take care. Hopefully all are doing well. Okay, talk to you later. Bye.